This video is an introduction to exponential functions. Our learning outcomes will be to graph exponential functions, solve exponential equations, and to solve applications involving exponential equations. Before we get started on exponential functions, one of the things that you might want to do is to review exponential rules and notation. So I have given you a couple of videos, and more importantly, I give you this outside one, outside of your textbook, that goes into a good explanation about all the different rules of exponents. I just want to cover a few. One of them that I want to cover is b to the 0 power. That is equal to 1. So it doesn't matter what the value of b is. The exponential to the 0 power will equal to 1. The other one is if we have b to the 1 power, the answer to that is going to be b. And then we have some negative exponents. So if we have b to the negative 1, that is going to be 1 over b. And again, if we have b to the negative n, we're still going to do 1 over b, but then it's going to be to the nth power for both of them. And 1 to the nth power is 1, so we end up with just 1 over b to the nth power. Notice the nth power is now positive. And then the other thing I want to talk about is going to be the product rule as well as the quotient rule. So the product rule says that if I have b to the m times b to the n, in other words, I have the same base but different exponents, then my answer will be b to the m plus n. And the video that I mentioned will actually tell you why this actually works. Likewise, we can have b to the m over n. Oops, sorry, that's not the one I'm talking about. If we have b to the m over b to the n, then we can get the same base, as long as they have both the same base, then we can have m minus n. And then the last one that I do want to talk about is actually b to the m over n, which we should have already talked about, that this is the nth root of b to the m, and we can write that as the nth root of b to the mth power. So that's our quick review of exponential rules and notation. I also want to talk about what if we had some numbers. So let's do an example of that. So I want to go over a couple of things that I find students making mistakes about. One of them is with the use or without the use of parentheses. So I just want to show you what difference those parentheses make. I always tell my students to think about that exponent affecting the closest thing to it. So for this first one, we're going to have a negative, which is not affected by the square, and then I'm going to have 3 affected by the square, meaning that I get to write that down twice. And we can see that our answer here is negative 9. Over here, the second problem I've written down, the 2, actually closest thing to it is a parentheses. So I'm going to write the parentheses twice. And each one of those are going to have the negative 3 on the inside. And we multiply negative 3 times negative 3, we actually get a positive 9. I wanted to make sure that we mentioned that when we were using parentheses and not using parentheses. The other one that I see my students getting confused about is 3 to the 1/2 power compared to 3 to the negative 2 power. Big thing to remember is that the negative means reciprocal, so I'm going to get 1 over 3 and then square it. Or you can think of it as getting the 3, squaring it first, and then getting the reciprocal. Either one will work. Over here we would get 1 squared over 3 squared, which is equal to 1 over 9. Over here we're going to have 9 to the negative 1 power, and that means reciprocal of the 9, which is 1/9. So both of those will be the same. Over here with this 1/2, remember that means the square root of 3 to the 1 power. So I just wanted to make sure we remembered which one we do reciprocals for and which one we actually get radicals. And then finally, I wanted to do the example of 27 to the 2/3 power, as well as 27 to the negative 2/3 power. So remember, the 2/3 power means I'm getting the cube root of 27 squared. And we mentioned that we could do it this way, or we can get the cube root of 27 first and then square it. Since I don't know what 27 squared is, much less the cube root, I would actually do this method and say I know the cube root of 27 is 3, because 3 times 3 times 3 is 27, and then I just need to square it, and that will give me a positive 9. Over here it looks exactly the same thing except for that negative. So I wanted to remind you the negative means 1 over 27 to the 2/3 power. And since we already know what the 2/3 power looks like, we can rewrite this as 1 over 9. Now let's turn our attention to graphing exponential functions. The very first thing we need to remind ourselves of what does our exponential function look like. So from our parent functions we had y is equal to 2 to the x, and our parent function looked like this. We actually know this point, that's 0, 1. And we actually know when x is equal to 1, this value right here will actually be 2. So we actually know a couple of points. Anyway, so what we need to remind ourselves is what happens when we put some of these transformations on them. So if I have y is equal to negative 2 to the x, remember this negative is out in the front. This is what we call a vertical reflection. So that means that our graph that looks like this will actually be reflected over the x-axis. So it's going to look something like this. So we can see that that's what our vertical reflection does. If we have y is equal to 2 to the negative x, notice it's inside or right next to the x. This is what we call a horizontal reflection. So it's going to reflect horizontally, meaning that it's going to have the mirror image here. So for a horizontal reflection, it'll still go through this point, but it will be coming around in this direction. So we can see that if we were going to do both of those things, that we would probably have something that looks like a negative reflection this way, and then a horizontal reflection to go the opposite direction. So it probably look like this. This would probably be 2 to the negative x as well as being negative. So let's see some easier transformations. So our parent function again was 2 to the x, and we saw that it would look like this. We know this point is 0, 1. We know this point here is 1, 2. Alright, so let's take a look at what does the x plus 3 do. So I'm going to put that in blue. So we're going to have y is equal to 2 to the x plus 3. Again, notice that it's inside with the x. So this is going to be a horizontal shift 3 units to the left. So it's going to be 1, 2, 3 units to the left, and this point will be right here. 1 over and then up to 2 would be right here, and we could still see it doing this number. Again, it only approaches the x-axis. It does not go to the negative side. So we just literally moved it 3 units to the left. Now let's compare that with y is equal to 2 to the x plus 3 like this. Notice the plus 3 is out here affecting the y value. So this is what we call a vertical shift 3 units up. So I will go from here 1, 2, 3. And then I would go over 1 and up 1. That would be up to 2. And then we would still see that our horizontal asymptote, instead of being at 0, would be up 1, 2, 3. So we can see that our graph will still go up like this, and will approach the y is equal to 3 asymptote line. So we can see the difference, that they all have the same shape except that they have been shifted to the left or upward. So that kind of reviews a little bit about what we should already know about graphing transformed parent function of the exponential function. So let's go in and talk a little bit about exponential growth. If we have y is equal to our 2 to the x, we can see that our parent function was continuously increasing and going all the way to infinity. We can see that it is a growth, exponential growth, because the y values are always getting bigger as the x values are getting bigger. Like I mentioned before, we know it goes through the point 0, 1. It also goes through the point 1 and whatever our base is, in our case 2. But we can see that information here, and it will always have y is equal to 0 as our horizontal asymptote. If we look at the decay ones, in other words, what if we had y is equal to a 1/2 to the x power? Well, we could still say that it goes through 0, 1. We can still say that it goes through 1 and its base, which in our case would be 1/2, and it would still have y is equal to 0 as our horizontal asymptote. And on the left side, it would actually be going upward. And we can see that this is actually decreasing. It's always decreasing. The numbers are getting smaller and smaller. Now, here's one thing I want to make sure I mention, is that we can see that y is equal to 2 to the negative x. Remember that negative exponent means we can write that as the reciprocal to the positive exponent. So we can see the relationship between getting it into a reciprocal one and a non-reciprocal one. So I just wanted to make sure we saw that. And then last but not least, I want to mention that an exponential function is 1-to-1 because it passes the horizontal line test, and we can see that right here. So no matter where we go, we're always going to get 1 point. Even though it starts looking like we're not, remember this is constantly decreasing, so it's getting smaller and smaller, and we're still only crossing 1 point at a time. And if we have functions that are 1-to-1 and they pass the horizontal line test, either way, right? If they are 1-to-1, they pass the horizontal line test. If they pass the horizontal line test, they are 1-to-1. And the big thing that gets us is that if we have b to the x is equal to b to the y, and because they're 1-to-1, then I know that x is equal to y. So we're going to use that fact in order to solve exponential equations. So one of the things that we just mentioned is that if we can get them to have the same basis, then I can solve an exponential equation. So if I have something that looks like 1/3 to the x power, and that's equal to 81, the question is, can I write this such that it has a base and an exponent? And if I can write this 81 with a base and an exponent, then we can just say that two exponents are equal if we can say that our two bases are equal. So I'm going to write the 1/3 as 3 to the negative 1, and I still have my x exponent. And then think about 81 being as 3 times 3 times 3 times 3, or 9 times 9. So this is the same thing as 3 to the 4th power. So notice that when we have exponents to an exponent, power of exponents, then we can sit there and say this is the same thing as 3 to the negative x, and this is 3 to the 4th power. Since I have the same base, then I can say our exponents are equal, and we can actually solve for x in that manner. So let's try it again with another problem. So let's say we have 2 to the x plus 4 and 8 to the x minus 6. So I can see that this is as basic as we can get in terms of a base. I can write 2 to the 3rd power to be the 8, and I still have my x minus 6 as an exponent. I still have 2 to the x plus 4. And what I want to show you, again, we have power to the power. So that means this is going to be 2, and then I'm going to multiply 3 times x minus 6. So that's going to give me 3x minus 18. And this is going to give me 2 to the x plus 4. And again, same base means we can have the same exponents, and then we can just solve for that. The last example that I want to show is that what if we didn't know the base, but we did know we had 2/3 up here, and we said it was equal to some number. So we're just going to put the number 5. So what we do know is that we can rewrite that exponential fraction as the cube root of x squared and say that's equal to 5. And then I can get rid of my radical by cubing both sides. And I can see that x squared, because remember our cube root and our cube undo each other, is equal to 5 cubed, which is 125. Again, you can also write it as just 5 cubed. Then I need to take the square root of both sides. This is going to give me x, and this is going to give me the square root of 125, which we need to know how to simplify. Now remember, 125 is 5 cubed, and we're getting the square root of that. We can write this as 5 squared times 5, and getting the square root of that. And we can see that the square root of 5 squared is 5, and the square root of 5 is the square root of 5. So I want to remind you to simplify your radicals. Finally, I want to talk about the applications of exponential equations. You're going to have two different types of compounded interests in terms of application problems. The first one is what we call compounded interest, because it depends on how many times per year that your bank will give you interest. So you're probably familiar with simple interest. That's when we get our amount and then we just multiply it times our rate in decimal form, and that's how much interest you get, and that's usually per year. What we're going to be talking about is compounded interest, that it will tell you how much money you have in the bank depending on how much money you put at the beginning. This is what we call the principal. And then we're going to put a 1 here because we want to make sure we get our money, our principal. And then we're going to add R over N, where R is going to be our interest rate and N is going to be how many times they compound my money. And it's going to be to the NT power. Now and T is in years, and N is going to be the number of times that it's compounded. So for example, if they say compounded monthly, then N is equal to 12. If they say quarterly, then N is equal to 4. If they say biannually, then that means N is equal to 2. So they give me money twice a year. I will tell you now that most banks will do it by quarterly. And sometimes they do monthly. So anyway, I just wanted to show you that. Things that they can ask you to solve for is how much money you get at the very end. You can solve for how much money you started with in order to get the amount of money that you want to. And then later on, we're going to solve for how long it takes to get that much money. But for right now, your job is to either solve for A or to solve for P. So I'll leave that there. The other type of interest that you can get is compounded continuously, and that is what I call APERT. So it's A, P, E to the R, T. Again, P is the principal, A is how much money you have, R is your percentage rate per year. So like if you had 8% interest rate, remember R would actually be 0.08. It's in decimal form. And T is in the number of years that happens. So in our case, again, you're going to be looking for how much money we should start with or how much money we have right now if we put our money in there for a certain amount of time. And later on, we'll start solving for T to make sure that we know how long we have to keep our money in there to get whatever we want in terms of guaranteed money at the end. And that concludes this video.